In this video, we're going to take a look at the area of a plane region. And so what we're going to look at here in particular is if we have a curve, y equals f of x, and the x-axis, and we want to know what's the area between those, what we can do is we can use some rectangles to approximate that area. So let's look at just some random function f of x. So this is my function f of x. If we're going to go from this value a to this value b, what we could do is, I don't know, let's use left rectangles. Left or left-hand rectangles. So what we're going to do is we are going to take this rectangle and we are going to use that as a height, and we can have this rectangle. The height of that rectangle is defined by the function value at that left-hand endpoint. This next one, the next rectangle over, we can use a function value here. And we can just continue doing that. With all of these, create a bunch of rectangles. And so if the width of these rectangles, pretend that those widths are all the same, let's call those widths delta x. Then this first rectangle we could call, or this first x value, we'll call that x naught, is a plus 0 times delta x. This next one, x1, a plus 1 delta x. x2 is a plus 2 delta x. x3 is a plus 3 delta x. x4 is a plus 4 delta x. x5 is a plus 5 delta x. And x6 is a plus 6 delta x, which in this case is our right-hand endpoint, b itself. So those are the different values that we have. If we're going to use equal widths, what is the width of each of those rectangles? Well, so that width, delta x, how did we get that? Well, we went from A to B, right? So B is this right-hand endpoint. A is the leftmost endpoint of our interval. So what we can do is we have the width is going to be B minus A divided by the number of rectangles that we have. And so then what is the area under this curve? Well, that area is going to be approximately the function value at A times delta x. Why? Well, that is giving us an approximation for the area of this rectangle, right? So we have the function value at A, right? So the height of the rectangle times delta x is the width of the rectangle. That will give us the area of this rectangle. And then what we're going to do is we will add the area of the next rectangle, and the next one, and the next one, and the next one, and the next one. So we're just adding up the areas of a bunch of rectangles. So we have f of a times delta x plus f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus f of x4 times delta x plus f of x5 times delta x. Now, why did I not use x6? Well, x6 is the right-hand endpoint of this rectangle, but the height of this rectangle isn't defined by that function value, which is up here. It's defined by this function value at the left side. And that will give us an approximation for that area. Another way that we could write this, then, is we could use our summation notation that we had looked at in our previous videos. We can say this is a sum from I equals 0 to 5 of f of x sub I times delta x. And so remember that x naught is just the value a, so that a we could replace with x sub 0. And so this summation would give us an approximation for the area. Now we used left-hand endpoints here. I could have used right-hand endpoints instead. So I could have defined this first height by the right hand, define the height of the next rectangle by the right hand, and then by the right, and by the right, and by the right, and by the right. So we could have done that, or we could have done midpoints. And so in our next videos, we'll look at an example, and we will do left-hand approximations, right-hand approximation, and midpoint approximations. So we will see you in our next video.